the organizers for inviting me here and setting my talk in the same session with two of my academic fathers, Gil and Nathaniel. So I would like to tell you today about our recent work, where we explored the problem of the heating-driven quantum systems. And we showed that the heating rate can have lower topological bounds in some driving protocols. So this work was done together with Etienne, Frederick, and Gil. So understanding heating is a very important problem. It's a very important goal, especially now when we have these large quantum machines with hundreds of qubits that should be kept at very low temperatures. And therefore, we need to develop better cooling devices that can cool the systems to low enough temperatures, and this is an active field of research. But we also need to develop optimized protocols that will minimize the heat production during the qubit operations. So the heating has various sources and different platforms, and here we want to focus only on the most basic and fundamental heating processes that should occur generically in driven quantum systems. So from classical thermodynamics, we know that if the change in the heat of the system is given by the change of the internal energy of the quasi-particles for a fixed volume. So if our protocol excites a quasi-particle to some high energy state, the particles will eventually collide, and this energy will be transferred into heat. So if we want to minimize this effect, we can make a protocol which basically moves the quasi-particles between the generated ground states, or basically along this minimum of the Mexican head potential. And if we want to minimize the heat further, we probably want to do it adiabatically, or as slow as possible, to minimize the probability for Landau-Zener transitions. So if we do all these optimizations, the question is, what would be the residual heating in this protocol? And so the minimal protocol that we can consider is basically a spin that rotates on the Bloch sphere with SU2 symmetry, and we basically slowly rotate it on the Bloch sphere. So this protocol, the dynamics of the spin will be described by the quantum geometric tensor. So this tensor has the symmetric component and the anti-symmetric component. The anti-symmetric part is the Berry curvature, and that would denote the geometrical phase that the spin, the wave function of the spin gains during the nearly adiabatic evolution. But there would be also the symmetric component of the quantum geometric tensor. And so this is the Fubini-2 symmetric. And this term will be associated with the heating and energy dissipation of the system. So the heating is a many-body effect. So here we consider a cloud of spins that weakly interact with isotropic Heisenberg interactions that preserve SU2 and some random coefficients. And in addition, all the spins are coupled to large magnetic field, which we can control externally. So you can think of this experiment as an MRI or an MR experiment, where basically the spins are some nuclei of the brain cells. Right, so if we slowly rotate the magnetic field as a function of time, so basically infinitely slow in the adiabatic limit, so then all the spins will follow the direction of the magnetic field, and at any time they will be basically in instantaneous ground state, and after a period they will come back to their exact initial position. However, if the magnetic field is driven not infinitely slowly, so then the spins will also precess. And because of the interactions, eventually they will not come back to their exact position after a period, but they'll be slightly tilted. And this state has a higher energy than the ground state. So that would be basically manifestation of the heating in the system. So if we focus on one spin in this cloud, its reduced density matrix is given by this thermal form, where beta is some effective temperature. And basically the goal of this work is to understand how much heat is produced in a period and what is, or which is equivalent to what is the change of this beta as a function of time. So the exact thermalization dynamics is hard. We can do exact time evolution, but that would be only for small systems, and it will not provide us with insights. So here we want to take an alternative approach, and we basically want to derive an equation of motion for this effective equation of motion for this reduced density matrix rho, and treat the rest of the spins as the heat bath for this specific spin that we pick. So basically the heat bath will be described by the spin fluctuations around some instantaneous magnetic field. So here we consider, we assume that the correlation time of the cloud is much faster than the frequency of the drive, so it's adiabatic regime. And we also need to assume the Markov approximation. And with these assumptions, we can write the master equation for a single spin. So the density matrix will evolve with the local Hamiltonian H naught, which is just B dot S. And there would be some Lindblad term, which includes the different jump operators for the spin. But basically, the goal of this Lindblad term is to thermalize the spin to the instantaneous thermal state with the heat bath. So if we do the evolution in time slowly, then the reduced density matrix of the spin will be almost the thermal equilibrium state plus some small correction, delta rho. And here we want to keep only the leading order correction, so basically the linear order in the frequency. So we can linearize the Lindblad equation with this small linearize in linear order to delta rho, and then the Lindblad equation has this form where gamma is some matrix that basically denotes the different relaxation rates for the spin to decay to the instantaneous ground state. So basically includes, the gamma denotes what is the time scale for the excitation to relax to the instantaneous thermal state of the system, of the spin. And the average heat that the spin produces per period can be just calculated from the change in time of the local Hamiltonian spin. And this term would be quadratic in the frequency, which basically makes sense because if we drive the system in the opposite direction, we still should get a positive heating. Okay, so if we do explicitly the calculation of this heating rate, we find that it has this form, and this form has a nice geometrical interpretation. So this lambda term defines some metric, which basically defines some surface in abstract space of the parameters, and then the heating rate would be given by the action along the trajectory that is gained, that is along a trajectory on this surface, which is parameterized by the magnetic field as a function of time. So, and explicitly, this lambda has this form, so it is proportional to the Fubini's 2D metric times some non-universal function gamma, which depends on the instantaneous gap and the relaxation time tau 2. And there would be additional corrections. So this is the zero temperature result. For finite temperature, there would be additional corrections which are exponentially suppressed. Okay, so now we want to use this form to find bounds on the heating rate. So basically, we want to use this relation between the quantum geometry and the Berry curvature. And this relation will make sense in the topological protocol where the Berry curvature makes sense. So one example of such a topological protocol is a topological frequency conversion. So in this case, the spin is driven by two magnetic fields, B1 and B2. And this magnetic field slowly oscillates as a function of time with two frequencies, omega-1 and omega-2. And the spin as a function of time will do some complicated trajectory. So it will basically follow the total magnetic field, and it will do some complicated trajectory on the block. So this paper showed that this protocol is actually has an interesting property that it will give rise to an energy transfer from B1 to B2 as a function of time. And it is some complicated nonlinear effect that is mediated by the rotations of the spin. And what was derived in this paper is that the rate of the energy flow between B1 and B2 is given by the product of the two frequencies, omega-1 times omega-2, times some number c divided by 2 pi. Okay, so what happens when the two frequencies are incommensurate? Well, in this case, this number c, in this case, the spin, the trajectory of the spin becomes infinitely long, and eventually the spin covers the whole Bloch sphere. And in this case, this number c becomes an integer, which basically denotes the total solid angle that the spin covers. So one way to parameterize the incommensurate regime, one way to describe this incommensurate regime is parameterize the ratio between the two frequencies by an integer n. And so as the larger is n, the longer is and the denser is the trajectory of the spin. And eventually, when we go to this limit of n goes to infinity, the trajectory becomes infinitely dense. In this regime, we can replace the line integral along the trajectory by the surface integral over the entire two-dimensional surface. And we verified that this result, that the convergence is pretty fast. So basically, around n equals 7, the frequency conversion converges to the value for n goes to infinity. Okay, so now when we, in this n goes to infinity limit, the dissipation rate can be written in this form. So now we replace the line integral by the surface integral, and we also explicitly write the expression for this lambda, for this metric. And so let's try to derive a bound on this heating rate. So let's start with a simple case where the off-diagonals of this quantum metric are averaged to 0. And this is actually the more common case of this topological frequency conversion protocol. So in this case, we basically can replace the quantum metric in this expression by the absolute value of the Berry curvature. And this expression has a nice topological not a nice geometrical interpretation, and that's why we call this bound the geometrical bound. Now, if we can remove this gamma function outside of the integral by replacing it by some minimal value over the entire domain, then we can get basically inside of the integral we'll also only have an integral over the Berry curvature. And that gives rise to the second bound, which is proportional to the absolute value of the chair number. And this is exactly the same chair number as in the frequency conversion rate. So basically, the interpretation of this result would be that if we have a finite frequency conversion rate, so if the chair number is non-zero, that means that there would be some minimal heating rate in the system. Okay. So so here we numerically verify this result. So basically, this is the heating rate as a function of some parameter m, and this parameter m denotes the topological phase of this protocol. So when m is between -2 and 2, the system has a non-zero chair number, and the protocol is topological. And when m is lesser than 2 or greater than lesser than -2 or greater than 2, then the chair number is 0, and the protocol is trivial. Okay, so this plot shows the actual dissipation rate. So the brown curve is the dissipation, and the pale area is the geometrical bound. And you can see that these two bounds are pretty close. And the blue area is the topological bound. So if we start, let's focus first on the trivial phase where m is greater than 2. So in this case, the chair number is 0, and the topological bound is 0 as well. And also the actual dissipation rate approaches 0 very fast. However, if you look at the topological phase, where m between -2 and 2, so here the topological bound is not 0, but it's not very tight. And the reason why it is not tight is basically because of the fluctuations of the gap as a function of time. So in the second, so then we use a different protocol where we fix the gap. And here the topological bound is much tighter. Okay, so what happens when these off-diagonal elements of the quantum geometry are non-zero? Well, in this case, the bound is much more complicated, and it depends on the details of the drive. So it depends on the powers of the fields. And basically, that opens up possibility that we can find a protocol where the heating rate would be below the topological bound. But so far, we were not able to find such a protocol. Okay, and we also derived, just for completeness, we derived the upper bound for this system. So in principle, there is no upper bound on the heating because we can always drive the system back and forth and generate heat. And here we found that the upper bound is just proportional to the powers of the fields. Okay, so in the last few minutes, I would like to discuss the actual many-body realizations of this system. So far we discussed the heating using effective model based on the Lindblad equation. But it would be nice if we can verify these results on an actual many-body model in the thermodynamic field. So is it possible at all? Well, it turns out that it might be possible if we slightly change the model. So instead of a cloud of spins, we use a cloud of simple fermions. And we said that we keep the system at half filling, so there is on average 1 spin per side, but the spins can hop. And therefore, we can have in our Hilbert space states which have 0 spins and states which have 2 spins. And we also add random interactions to this system, so, such that the Hamiltonian that describes this system is given here. So here alpha is the site index, so it runs from 1 to n. And the magnetic field acts locally on the spin. But in addition, we have this interaction term, which basically connects 4 fermionic operators at 4 different sites. So alpha, beta, gamma, and delta. And the coupling coefficient is, we assume that it's random with 0 mean. Well, it turns out that this Hamiltonian is equivalent to a Hamiltonian of 2 SYK dots. One represents spin up and the other spin down. And the coupling between the SYK dots is given by the magnetic field and is modulated in time. So the beauty of this model is that it can be actually solved exactly in the limit, in the thermodynamic limit, where we take the number of sites n to be infinite. And in this paper, we showed that this is actually it is actually possible to analyze models of coupled SYK dots, which are driven in time, and that would be a useful method to study thermalization and heating dynamics of driven systems. And if you are interested in more details, you are welcome to my poster number 9, where I present this work. So the idea would be, so the idea why this model becomes simple to analyze is because the Green's functions get simple self-consistent relations in the thermodynamic limit. And we can use these relations to to basically evolve this Green's function as a function of time using the Kadanoff-Bane evolution. So basically, the basic principle would be to start with some equilibrium state of the system before we initialize the magnetic field, and then turn on the magnetic field and evolve this Green's function in the t prime direction. And we can extract the heating in this problem by basically looking at the effective temperature of the Green's function as a function of time. So the idea would be to test this model on different timing protocols and see where the results agree with the effective model and where the effective model based on the Lindblad equation breaks. So this is still a work in progress, and hopefully next time, if I will be invited, I will present you some data. Okay, so let me just briefly mention what would be the realizations of this model. So there are several realizations of the topological frequency conversion in different platforms. So we can use magnetic field spins, basically NMR or MRI experiments. There are proposals how to do it using circuit QED and superconducting qubits. And recently there were a few proposals how to do that in solids. So there is one work that suggests using wild semimetals, and recently we published this paper where we propose to do topological frequency conversion in rhombohedral graphene. Okay, so let me summarize. So I discussed heating in driven quantum systems, and I showed that we can study heating using effective models based on Lindblad equation. And using this model, we can show that the heating is linked to quantum geometry, and that gives rise to topological bounds in certain driving protocols. As a future directions, we can basically study this model in the full many-body case using SYK realizations. And another interesting direction is explore protocols that can give rise to heating which is below the topological bound. Yeah. Okay. Thank you.
Could you go back to the slide where you had the actual heating rate be close to the topological bound? Yeah, this one. So yeah. It seems like so you modified the model so that the topological bound is kind of a tighter bound, but it seems like this actually increased the heating rate, right? So like if your like optimization procedure is different and like you want to just like decrease the heating rate as much as you can, like what should you do?
Yeah, so that's a good question. So first of all, I should say that in this model we fix the gap, but that makes the model very non-local. So, so it was a bit pathological case where we just wanted to verify that the main reason why we have this discrepancy is because of the variations of the gap. So if you can find, yeah, so we are trying to find, basically we try to find a better model that would minimize the heating rate, that would minimize the heating rate and be optimal, but so far we couldn't find one.
Is there any like principle clear for like what kind of things should you do, even if you can't find the optimum yet?
So you want the gap to be large, right, compared to tau, to the relaxation time, and you want it to be as flat as possible. Okay. So if you can find a model where the gap has very small variations, and it is topological, so that would be the best, the optimal case for the protocol to work.
Other questions? Yes? Yeah.
So in your Lindblad, you separated the density matrix into an instantaneous thermal and a rest, right? So is that instantaneous thermal with a time-dependent temperature that depends on the heating rate?
Yeah, right. Yeah, so the assumption here is that the temperature will change much slower than all the time scales of your protocol, right? So you can basically assume that the temperature is fixed for each period. And then it slowly grows. So you can actually, if once you know what is the heating rate, you can know what is the change in temperature if you know the heat capacity of your system.
Solve it like self-consistently.
Not really. So yeah, so sort of. So for each cycle, the temperature is fixed, but it can grow as a function of time. You know, if you take many cycles, basically. So here in this, what I showed here is basically the assumption is that the temperature is still low, such that we can neglect it. But in principle, there will be additional corrections that I didn't present here, where the temperature becomes significant.
Thank you very much for the nice talk. I have first one remark. So in the geometrical interpretation of heating, could you put that slide? Maybe it's easier to. So.
This one.
So this the first expression W bar D, it kind of looks like the kinetic energy that you would get by using that lambda ij as a metric or something. So there's a natural lower bound that you get, which is the geodesic, right?
Right.
So that's one. I don't know how that compares to the topological one. And the other question, is a question is in the next slide where you show this now appears as an average over phi1 and phi2. How do you get from the other expression to this one?
Yeah. Okay. Right. So first regarding your comment, yeah. So that's a very good point. So if you have right, so if you want to minimize your, you say you have some periodic protocol, you want to minimize it, then you probably want to drive along the geodesic of your metric. But actually, right. So but then the best would be just contracted to zero, right? So you just take your trajectory contracted to zero. That would be the best. So here in this topological frequency conversion protocol, you actually cover the whole sphere. So you can never contract it to zero. Okay, so then regarding the bound, so how do I get to the surface integral? So that's basically related to this question. Yeah, so it's sort of if you average so you want to average over the trajectory, right? So that's
How does it go?
yeah. So you want to average over the trajectory, but you can actually show mathematically that that's equivalent to averaging over the two phases of the spin, basically. So like if your trajectory is really quasi-periodic, that would be equivalent. And here we verify that it actually works, numerically.
So then this W then becomes something like the Dirichlet energy for a map to projective space. So the obvious minimum is the one where you saturate the bound and you get the German.
Yeah, right.
But there are other minima, not minima but extrema, and these correspond to harmonic maps. This is more a remark than that. So and those minima will also be quantized, and it's kind of related.
I'll be happy to hear more about it. Maybe we can chat later.
Thank you.
If there are no any more questions, I would say and thank